Okay, so this is your final assessment on Newton's second law. Make sure to look at the point values for each question as an indicator of how much work is involved in that question. If it is out of 2 marks, do not do 5 marks worth of work. You are definitely doing something wrong. Okay, so if it's only out of 2, show 2. Here's something that would suck for a 2-mark question. Let's say I do all the work, I write down the answer, and I don't put the right number of significant digits or a vector on it, and I lose half of the marks for that question as a result. That would not be fun. So, please make sure you remember things like significant digits and vectors on all of your answers. Okay, so 1 and 2, very simple Newton's second law questions. Don't overthink them. Okay, number 3 is basically just asking you to find the vector components. Right? If I'd asked you to do that in the last unit, you'd be done in 30 seconds. Okay, so you've got an angled vector and the angle. Just find x and y. That's all you're doing for number 3. Okay, number 4 is giving you 3 different free body diagrams and is asking you to calculate the acceleration of the object in each case. All right? So think about what you have to do. If you're given the free body diagram, what's the next step? How do I get to acceleration? Okay, you're doing that for each of these 3 situations. So it's like A, B, and C. All right, the vectors are on there. Okay, it's always 60 and 40. All they're doing is changing which direction the 60 and 40 point. And it does ask, what is the angle relative to the x-axis? Okay, so your answer should say like above x or below x or whatever, okay, referring to the x-axis. Number 5 is a bit of a different question. We've kind of done questions like this, but this one's a vector trick, is what I'll tell you. It's less about Newton's second law and more about vectors. That said, Newton's second law is still part of it. Okay, so it's this sphere that's 36.5 kilograms is being acted upon by 2 forces. One of those forces is 113 newtons, and it's directly along the positive x-axis. So that's the positive x-axis. Okay, so your first force is that way. It's asking you, what is the magnitude and direction of the second force, such that the sphere experiences an acceleration of 3.96 meters per second squared, 21 degrees above the x-axis. So you can probably use that to get something that will be useful for finding a missing force, since it's, after all, acceleration. And they probably gave you mass here earlier in the question, and those 2 things can help you find something useful. But remember, it's a vector question as well. All right? Number 6, people really overthink number 6. Okay, so I want to give you some tips here for number 6. This spacecraft has a mass of 4,160 kilograms. It can only fire 1 engine at a time, and they are either on or off. Okay, there's no throttle. So we're simplifying this. Okay, when the engines are on, they can exert 68,000 newtons worth of force. All right? If I were to fire engine A, which way would it push the spacecraft? Right, to the right. Okay, yeah, forward, whichever. Okay, so think about which engines you would need to fire in order to cause the change they're asking for in the question. So in this question, they want to no longer go to the right or forwards at 2,170 meters per second. They just want to go 90 degrees clockwise at twice that velocity. So you kind of have to do 2 steps. You have to stop the spacecraft, and then you have to make it go the other way, okay, twice as fast as it was going at the beginning. Okay? All you have to do is tell me which engines to fire and how long to fire them for. So there's a bit of acceleration stuff in this question along with the Newton stuff. Okay? That said, it's really, none of it is really mathematically difficult. Okay? You're told how much force is involved. We're in space. There's no friction. Don't overcomplicate it. Okay? All right. Question 7, okay, and question 8, same types of questions. We've done 2 examples of each of these in class. Okay? In both of these questions, the sign and the street lamp, we're just hanging there. Okay? So think about what kind of example of question that is. We've done a number of those. The thing to watch out for here is that in part A, the angle is 120. In part B, it's reduced to 90. Right? What throws people on this question is they don't like the number they get. So if you look at that number and go, ooh, I don't like that, you probably did it right. Okay? People just don't like it when they do it. Okay, especially for part B. All right, and then 8, like we said, same kind of question. Okay, question number 9 is very much like the question we did on the quiz. Okay, it's a box, it's moving along the table. It's not an inclined plane. Okay, people do this question wrong because they think it's an inclined plane. Number 9 is not an inclined plane. All right, it is just a box being pulled at a constant speed, okay, along a table, okay, or along a floor. All right, and they tell you some of the information about the pulling force and the angle of the, you have to find the angle of the pulling force, all of that kind of stuff. Okay, so just make sure you do it as a question where something's moving along a level surface. Okay, 10 and 11 are both inclined plane questions. Watch out for this. They both give you the box in newtons, not kilograms. Okay? And when they ask for the component of gravitational force acting down the plane, that's F parallel. Okay? It's a really wordy, confusing way of saying, what's F parallel? So for part A, for both 10 and 11, calculate F parallel. Okay? That's what you're doing for those. All right, you got the rest of the class to work on that. If you got questions, I can be cryptically helpful.